Hello YouTube! So today we're going to be going through some of the break work, just one specific assignment, and going from there. If I pause awkwardly for extended periods of time, it's because one of the people in the call has asked me a question, and I will repeat that question so you can hear it. That being said, for the people in the call, please ask questions. So, what we're basically doing for this one is putting together our old stuff from the forces unit with our new stuff from the kinematics unit. The only really big difference, well, there is no real big difference. We're doing either one or the other, and it's just sort of remembering that you can do one of them to fill in some info for the other. Something that this doesn't have is using kinematics to figure out acceleration so you can find a force. What it does have is the direction, going the other way. So using forces to figure out accelerations so you can do kinematics. Which was a little bit of an oversight on my part. So to start with, what on earth? Oh, yeah, fine. We've got a 40 kilogram box of penguins and it's sliding down a frictionless hill that is 20 meters long. Okay, so I'm just going to start writing stuff down. We've got that our mass is 40. We've got 20 meters for the length of our hill. So that's going to be our displacement for our first section. The angle is 30 degrees. At the bottom of the hill, we've got sort of the second section. So section 1, section 2, and then it looks like they fall. So we'll call that section 3. At the bottom of the hill, there's a flat grassy section before the edge of the cliff with a coefficient of kinetic friction of 0.8. So this has mu k equals 0.8, which they slide on for 2 seconds. So this section here, the time for the second section is 2 seconds. Before if they fall off the edge of the 15-meter tall cliff. Oh, these numbers are going to be terrible. I do not know why I did this. This is delta y for our third section. How fast are the penguins going at the bottom of the hill? Okay, so none of this stuff is going to matter for part A because we're just being asked about to the bottom of the hill. So that's great. This is all just asking stuff about section 1. And then honestly, based on how it looks for the setup, we can probably forget everything after that because the speed of the penguins at the bottom of the hill is going to be the speed of the penguins when they begin sliding across the grass. And then we can just forget all the stuff about the hill. So if we think about our penguins, we don't know an acceleration. If we're trying to figure out speeds, the only real way we know to do that so far is with kinematics equations. So if we set up our variables, we've got our displacement for our first section is 20 meters. We've got that our acceleration we don't know, and this would be parallel to the hill. We know that our initial velocity is 0 because they begin from rest. So Vx1, I guess, not. V1 naught would probably be the way to write that. I'm going to write that as V1 naught. And then V1 for the final, we don't know, but we're looking for it. And the time, we also don't know. So in order to figure this out, just like always, we're going to need 3 of the 5. We only have 2. So we need to find out either our acceleration, our final velocity, which would be our answer, or our time. But we also have this information about the hill angle. And if you think back to last unit, we can use that to find an acceleration by setting up a free body diagram and doing Newton's second law. I'm going to skip a little bit of a step and rotate it already. So there's going to be some normal force from the hill going up, and there's going to be gravity going down at an angle, but that's sort of the only force that there is. So we'll have mg sine theta going along the hill, and mg cosine theta going into the hill, because those are the 2 components for hills. A lot of this stuff is sort of old, and I'm going a little quicker because of that. What I can then do is set up sort of my perpendicular forces and my parallel forces to try to find my acceleration. Now, my perpendicular ones are going to add up to 0. It'll be Fn minus mg cosine theta equals 0. And if there was friction here, I'd have to care about that, and I'd need to use it to get the normal force. But there isn't, so I don't, so I won't. In the parallel direction, the only force is mg. and mg times the sine of theta. And mg sine theta will equal mass times the acceleration. Well, if I just divide each side by mass, what I'm left with is that my acceleration is going to be g sine theta, because there's mass on both sides. So this is going to be g times the sine of theta, which is 5, because sine 30 is a half, but should double check that. So 10 sine 30 and 5. Great. So now I've got my acceleration, I've got my displacement, I've got my initial velocity. I can use that to find my final velocity. I need to pick a kinematics equation that's got all 4 of those things, at least if I want to do it in one step. So we're going to do that our final is equal to our initial squared plus double our acceleration times our displacement. And this one is actually basically also already solved as long as I just square root it. So what we're left with is that our final velocity will be equal to the square root of nothing plus 2 times 5 times 20, and then we'll have to square root that. So I'm actually not going to write this as like a number because like as a decimal number, just because I want it to be a little more exact as I go. We're going to have 2 times 2, which is getting square rooted, and then we're going to have 10 times 5, so it's 2 times 5, which is 10, and then the leftover root 2. As a double check, it's 200, so 200 divided by 100 is, yeah, so it's root 100, 10 times root 2. And you can throw it into a calculator and get just decimals if you prefer that. But for me, it's nicer to write 10 root 2, and I wind up getting a more exact answer a little later on. I've decided. Are there any questions so far on any of that? Okay. Let's do the next part. So how far away from the cliff do the penguins land when they land in the river? So this is one of the ones where it's not quite as straightforward because there's going to be a few different steps. There's going to be a few different things to think about. Generally speaking, you can either start at it from the answer and then be like, what would I need in order to get the answer? Or you can start at it from what you have and be like, what can I get based on what I have? Any preference between the two? Okay. We just figured out this speed at the bottom. Let's see what we can use that to figure out and what that might be, how that might be related to how far along the penguins fall. Well, in particular, they're going to be traveling sideways. And so what we're looking for is our sideways displacement for our third section. I'm actually going to work backwards from that because there's not a lot that we have to work with there, and that makes it a lot easier to see like what we can do. So if we want to get this, the only relationship we have for the x direction for section 3 is that Vx times time is going to equal displacement because it's going at a constant velocity in the x direction. Because nothing's accelerating it in the x direction while it's in the air. So if I want to find my displacement, I'm going to need to find my Vx, and I'm going to need to know my time. We don't know either of those initially. I guess this would be v3x, because it's the x component of the third velocity. And then that'll give us our displacement. So we've got 3 unknowns, and that's not great. We do need to figure out 2 other things before we can get it. Well, if we look at the y direction, and you did this for the Nerf Dart lab, if you look at the y direction, we actually have a bunch of givens. We have that delta y is equal to 15 meters. We know that it's effectively actually launching with an initial velocity of 0 meters per second in the y direction because it's being launched sideways. So v3y naught is 0. And we also know that the acceleration is just gravity because it's going down. I've set down to be positive for this just because I don't want to futz about with all the negative signs. If you wanted to make it negative 15 and negative 10 meters per second squared for the acceleration, you totally could and it would work. And so what we can do is we can take these three, and that would give us the final y velocity and the time. We don't need the final y velocity, but we could theoretically get it. All right, great. So that'll get us the time. So I have a path to get this one. Now I need to figure out how to get the velocity at the sideways velocity. Well, do I know anything about this box that I haven't used yet? Well, I just figured out that right here, the velocity for the second section at the beginning is 10 times the square root of 2. And so if I look at my second setup, what that'll look like is delta x, acceleration, time, our initial velocity for the second section, and our final velocity for the second section. Well, our final velocity for the second section is the velocity right here, which is when they launch off the cliff. So this is actually going to be the same thing as our x velocity for our third section, v3x. So if I can figure out this, I can get v3x. I don't know my displacement. I don't know my acceleration. I do know that my time is 2 seconds. I really hope I didn't make it so that they stop before they reach the cliff. I tried fairly hard to do that, and I'm just realizing I think I might. No. All right. 1 sec. I can fix this. 0.6. Excellent. Great. Wonderful. All better. Mu is 0.6. I think they have a negative velocity if we solve it out. We know our time. We know that their initial velocity is 10 root 2. We don't know their final velocity. So if we could get either their acceleration or the displacement, we'd be good to go. But we don't have that yet. Just like with the last bit, we can get the acceleration by thinking about the forces. We know that if we draw out a free body diagram, there's going to be normal force going up, there's going to be mg going down, and there's going to be a force of kinetic friction going to the left. If we look at our perpendicular direction, we'll have that our normal force minus mg is equal to 0, which tells us that our normal force is just going to be mg. In our, I don't know why I'm doing perpendicular parallel for this. In our y direction, we'll get that. In our x direction, what we'll get is that our force of friction is the only thing that's making it accelerate. So if we know how big our force of friction is, we can figure out what the acceleration is because that's the only thing. Now we need to figure out our force of friction. Well, we have coefficient of friction and it's moving, so our force of friction is going to be equal to our coefficient of friction times our normal force, which means that our force of friction is going to be equal to mu k times mg. And I can take this and I can plug it in up here and we'll have our acceleration. Mu k times mg equals ma. This is taking this with it plugged in and bringing that over here. Dividing each side by the mass will give us that mu k times g is equal to our acceleration, which means our acceleration is 6 meters per second squared. Coming over here, I do have to be a little bit careful with that 6, and I actually should have been more careful with that here. This should be negative because it's backwards. This should be negative. This should be negative. This should be negative. And so our acceleration should be negative 6 meters per second squared. Now I know my acceleration, I know my time, I know my initial velocity. The only thing I need is my final velocity. So what I can do is set up Vx equals Vx naught plus acceleration times time, because that's the equation that relates all four of those. When we do that, we'll get Vx equals 0 plus negative 6 times 2. Oh, sorry, not 0. 10 root 2. So we'll get 10 root 2 minus 12, which is like 2.1-ish or something, but 2.14. Which gives us out 2.14. I'm going to stop being so careful about writing out things because it's starting to get a little bit more effort with the subtraction in there as well. This is our Vx while they're in the air, because this is the velocity that they're going when they leave the cliff. What I can do is I can take this and I can bring it over to here. And if I do that, I now know that this one is whatever I solve this out to, which I do actually have to do. So for our y direction, all right, let me number things. This is step 1. Step 1. Step 2 is to think about the second thing. Step 3 was to get our acceleration. Once we've got our acceleration, we can bring it back over here. And so this sort of like arrow here is step 4. Step 5 is going to be getting our time, which we've got acceleration, initial velocity, and delta y. So we're going to do delta y equals 1/2 at squared plus v y naught times t. V y naught is 0 in the y direction for this one. So all I have to do is multiply by 2 over a, multiply by 2 over a. That gets me that my double my displacement divided by my acceleration is equal to my time squared. Square root both sides, and we'll get that our time is equal to the root 2 times our displacement divided by our acceleration, which is root 30 over 10, so root 3. Root 3 seconds. Now what we can do, we're almost done, is take this, bring it up here. When we do that, for our x direction, this is sort of our step 6. For our x direction, we know that our displacement is going to be our velocity times our time. Our velocity was 2.14. Our time was root 3 seconds. So when we multiply those two out, we get 3.7. So they go 3.7 meters away from the base of the cliff. So, bit of a journey. Before we move on to the next part, which honestly is easier. It's just sort of a forces review, so you have to actually do a net force. Are there any questions? Okay. So, they hoist up their sails, which they apparently had with them, making an angle of 10 degrees with the vertical. The wind places a constant force of 200 newtons on the sail, while the river places a resistive force of 100 newtons on the box. How long will it be before the box reaches its maximum speed of 30 meters per second? So we're looking for the time. We know... We know the initial velocity. If you said that the initial velocity was 0, I would have given you full credit. I just realized that the initial velocity for this one is actually going to be the velocity from here. So it's going to be the 2.14, because disregarding the fact that they're going to like slosh into the water and slow down that way, they'll be moving at that speed before they get started. Again, if you had chosen 0, yeah, you're fine. That's a pretty reasonable assumption. It's also a very small difference between the two. It's off by 2. For our free body diagram, our sails are going like this. The wind is going to be pushing the sail like that. So the force from our winds is going to look like this, which means that this angle is 10 degrees, which is perpendicular. This adds up to 90, so this is 10 because this is 90 minus the 10. For some reason, my brain for explaining geometry is not quite on right now. Yeah, so this is 90 minus 10, which means it's the same as this angle, because this is also 90 minus 10, which means that this angle and this angle add up to 90, which means that this is also 10. Geometry is bad sometimes. It is also part of our life. We've got that the force from the wind is times the cosine of theta. 10 will be our component that's pushing us along. We've got that our force from our wind times the sine of our angle is going to be the part that's lifting us up. We're also given that there is a force from the river that's 100 newtons backwards. We know that the force from the wind is 200 newtons. There's going to be some buoyant force. If you said normal force, that's fine. And some force of gravity going down. It's not a big difference between buoyant and normal. They'll function very similarly. It's just that it's floating, so that the fancy word for that is buoyancy. So that's our free body diagram for this one. The reason I'm doing that is because if we want to find our time, we know our final velocity, but we don't know our displacement, and we don't know our acceleration. So once again, in order to get 3 of the 5, we just have to get the acceleration. So this is just like 3 or 4 repetitions of the same thing. Get the acceleration, call it a day. In this case, our x direction will look like we've got force of the water times the cosine of theta going forward. We've got the force of our river going backwards. That will need to equal our mass times our acceleration. If we divide each side by the mass, we're done. So the force from the water times the cosine of theta, or the wind times the cosine of theta, minus the force from the river divided by our mass, which is going to be 200 times the cosine of 10, which is almost 200, honestly, minus 100 divided by 40. And that's going to be our acceleration, and that's going to equal 200 cosine 10 minus 100, close parentheses, divided by 40 equals 2.4 meters per second squared. So 2.4 meters per second squared. And because we have an initial velocity, a final velocity, and acceleration, and we're looking for a time, Vx equals Vx naught plus AT. Subtract each side by the initial velocity. We'll get Vx minus Vx naught equals AT. Divide each side by the acceleration, and we're done. Final velocity minus our initial divided by our acceleration will be the time, which is going to be 30 minus 2.14 divided by 2.4. Which is 11.6. I heard the door open, which I assume means that there's a cat in here now, but who knows. Questions on that one? Okay. Next one is very short. How long will it be before they get to their home 4 kilometers down the river? Well, their maximum speed is 30 meters per second. And this is 4,000 meters. And it's at a constant maximum speed of 30 meters per second. So velocity times time equals displacement. We're looking for the time, so just divide by the velocity. and we'll get that our time is equal to our displacement divided by our velocity, which is 4,000 divided by 30. If you want to be really careful about that, what you could do is figure out how long it takes them to go some starting distance from like that 11 seconds that they traveled. They go an average velocity of about 16 meters per second. So you could take that 16, you could multiply it by the 11, that would get you the distance, or you could just use kinematics to get the distance that they go, subtract that away from the 4,000 and be really, really careful about it. But given that the answer is 133, the fact that it will technically take them maybe 6 seconds less than that is not super relevant. All right. So to celebrate reaching home, they slide up and down a hill with friction. They slide from the bottom of the hill, stop, and turn around. Okay, so they go like this, and then they go like this. How will the time it takes them to go from the bottom to the top, so this one, and we're looking about time, compare to the time from the top to the bottom? So, on the way up, friction will go down. So we'll have our force of friction. I'm actually going to rotate this. On the way up, we'll have our force of friction going down the hill. We'll have gravity going down the hill, and we'll have our normal force. Versus on the way down, we'll have our force of friction going up the hill. We'll have our gravity still going down the hill. And we'll have our normal force going up the hill. Okay. So, taking a look at this, if we want to try to figure out about the time, we'll need to think about all the kinematics variables. Their displacement for both sections is the same because they're going, this is delta x for one of them, this is delta x for the other. Technically, they're like one is plus, one is minus, but that shouldn't matter too much. The final velocity for this one and the final initial velocity for this one are both 0. So one of the velocities is 0. If we want to do our kinematics stuff and we want to think about it that way, we'd either need to know about how their other velocities compare to each other. If we knew about energy, we could use that to figure it out and it would be pretty quick, but we don't. So can't think about final velocities. Or we would need to think about the times, which if you skip ahead, that's what that's what we're trying to figure out. So our last thing that we can think about is the acceleration. The force for this one, the two forces are working together. You've got force of friction negative and negative mg sine theta. And so what you'll wind up with versus the other one where you've got positive force of friction minus mg sine theta is that this first one has a bigger negative acceleration. So if the acceleration is bigger, but the displacement is the same, and one of the two velocities has to be the same, then it'll take less time because there's more acceleration getting it to create that change in velocity, or causing it to travel that set distance. That's the big one, getting it to cause that set distance in less time. So answer, it takes less time to go up because one velocity is the same. The displacement is the same. But the acceleration for the first one is bigger than the acceleration for the second one. So the time is smaller. And that way we've talked about 3 of our 5 kinematics variables, and so we're allowed to answer about our 4th one. We can use that same logic and that same setup to answer about our 5th one. It's a little easier to think about with, well, I guess either one is totally fine. For this next question, where we're being asked if they are going faster at the bottom, so the question is basically saying, this is them on the way up. The initial velocity on the way up is this thing. The final velocity on the way down is this other thing. The initial velocity on the way down is 0. The final velocity on the way up is 0. So they're asking us which of these 2 velocities from the way down or the way up is bigger. Really easy with energy, which is our next unit. For us, it's a little bit trickier. We do have to actually think about 3 of the 5 still. So thinking about our 3 of the 5, we want to find out about final velocities. We know about the accelerations, and we know about the times. But there's different accelerations and there's different times. So I actually want to try to avoid thinking about both at once, because if 2 things are changing, it might be more complicated to figure out what the end result is. So I'm going to try to find an equation that only has displacement, the final velocity, the initial velocity, the displacement, and the acceleration. The reason I'm doing it this way, or what you could do instead, I'll put the alternate solution down at the bottom. You could also think of it using an equation that has time but no acceleration. Because you know about the time. So I know that this one is the same. I know that one of these is the same. And I know that this one is that A1 is bigger than A2. So if this number is bigger and this number is the same, this number will also be bigger. So we've got bigger plus the same thing means bigger for 1. So because, the initial velocity for 1 is bigger than the final velocity for 2 because the displacement is the same. There are 2, the final velocity from the first section is equal to the initial velocity from the second section, and the acceleration for the first section is bigger than the acceleration for the second section. An alternate way to do it, or think about it with another equation, would be using the times that you just got for the last part. We could say that their displacement is equal to their average velocity times time. The reason that that one's kind of nice, a longer time to go the same distance means that the average velocity must be lower. So if the average velocity is lower, one of the velocities has to be slower at the end, because if you add the 2 together and divide by 2, you need a smaller number to be adding to 0, not a bigger number to be adding to 0, if that makes sense, hopefully. If it doesn't, hopefully the other way makes sense. Did that make sense for those 2? Would it be helpful to get another explanation or a slightly different explanation? Sort of that process of how do you answer conceptual questions is one that we're a little bit newer on. This is similar to the types of questions you could expect to see on the AP exam. In fact, I might have literally, now that I'm thinking about it, stolen this question from the AP exam and made it a box of penguins instead of a box of just a box. For E and F, anyway. Cool. Well, that's it. Thanks for sticking around doing the break work. Clocked in just under 40 minutes, so my prediction wasn't too far off. I'll get this uploaded to YouTube if you want to rewatch it, and you should be all set for credit. Hope you have a great lab.